All right, you made it. Final lesson of Unit 3, all right, which means we're looking at our last function, which is exponentials. All right, so just like we did in the prior lessons, we're going to start with 6.4, right? I can write the equation of exponential function from a table of values, all right, and then we're going to try to translate that into some other situations. Now, this various context for exponentials, all right, we're going to talk about some very specific things, all right, and we'll talk about those in just a moment, all right, but just know that this is going to require you to learn some information, right, and to be prepared to know how to use that information, all right, on your assessment. So when we get to that page, there's going to be definitely something I want you to highlight, star, because you're going to have to study that, all right, pretty well to make sure you're ready for your assessment. But to get us started for today, let's go back. It's been a while since we've looked at exponentials. So to get us thinking about that, we're going to do the opener. We have two graphs here. All right, so what I would like you to do is pause the video, write the equation of those two exponential graphs. All right, flip the video back on, and we'll see how you did. I'm waiting. Go ahead, really. Do it. Yeah, yeah. Sure, yes. All right, let's take a look. All right, so once again, and I'll just kind of cheat a little bit here that we know y equals b to the x plus k is our form, right? So k is our floor. So if I look at the first equation here, right, we can see that -7 is our floor. All right, so I've got half the equation, all right, just by identifying my floor. Now, the other thing is I need to know if it's going uphill, which this one is, or downhill, like this one is. And that tells me my b value is going to be either bigger than 1 or less than 1. And if I look, I can look at how these changes are occurring here. And I can see that when I look at this particular problem, I go 1, 3, 9. I'm increasing by multiplying by 3, so there's my base. So that's 3 to the x and then -7. All right, if we move to part B here, all right, there's our floor, all right, so y equals something to the x and then plus 3. Now, this is going downhill, so now I know I have a number between 0 and 1. Remember, our base is always going to be a positive number. So if it's going downhill, that means I have a number between 0 and 1. And if I look at these rates of change, let me write these in here, and I suggest that you write them in too, because it really does help you see the pattern here. 8, 4, 2, 1. So what are you doing? You are dividing by 2. So what is my base going to be? It's going to be 1/2. All right, so there's my equation. Y equals 1/2 to the x plus 3. And remember, if the x is the exponent, it is exponential. All right, so now, okay, so moving to tables here. All right, standard 6.4. How can you tell if a table is exponential? All right, so a couple things, right? The rate of change involves a multiplier or divider, right? We said the other big hint, right? The other big hint was the floor, all right? And the way we see this, right, is we see, all right, decimals, all right, I get that CI in there, there we go, decimals. Let me try that one more time here, decimals, there we go, all right? As a giveaway, because if we're approaching the floor, we're gonna get really, really close to a number, all right? And the way we see that in a table, right, is we see those decimals, right? 4.1, 4.05, 4.0005, 4.0001, right? So that's a giveaway. All right, now let's look at our table here. So once again, all right, let's see if we can transfer some things that we've been talking about. So we always want to look for a turning point first, all right? And when we scan, all right, this table, don't see a turning point, okay? I do see those decimals, right? So it's like, maybe this is exponential, right? So now let's look at those rates of change, all right, to see if we can confirm that, right? So all my x's are going up by 1. Now, once again, some of these decimals are hard to see, but this is an increase of 0.25, and this is an increase of 0.5, and then an increase of 1, and then an increase of 2. So I can definitely see that it is not constant, right? These are not equal. So non-constant rate of change means, okay, I am throwing out absolute value, I'm throwing out linear. I don't see a turning point, but it still could be quadratic, right? But I can see that these aren't increasing by the same amount. So then I'm looking for a multiplier. And what my multiplier is I'm increasing by multiplying by 2. All right, and I can see that my values are going up, so it's going uphill, so I know my b value should be 2. Now I'm looking for that floor. And as I look, I'm getting really close to -4, -3.75, -3.875. So I'm getting really close to -4. All right, so there's my equation, 2 to the x minus 4, just like that. All right, let's flip the page and look at number 2 here. All right, so once again, All right, once again, we'll scan that table. Okay, I don't see a turning point. All right, so now I'm like, okay, probably not, definitely not absolute value, probably not quadratic, but could be. All right, so we want to jump in and look at those rates of change to see what we have. So all of my x's here I can see are in fact going up by 1. Now let's look at those change in y's. 29 to 11, I go down 18. And 11 to 5, I go down 6. So right now, I know for sure it can't be linear, right? Not a constant rate of change. So linear, absolute value, definitely out the window. Okay, now let's continue with those rates of change to see if we have a multiplier, right? Or if it's changing by the same value like a quadratic would be. And then I go down 2, and then I go down 2/3, all right? And then this is like, I think 2/9, all right? And on and on and on. So now when I look, right, this is plus 12, plus 4, plus something. So definitely aren't increasing the same way, so that means it can't be quadratic. So now I'm looking for it to be exponential. Now, my numbers are going down, right? And we know if it's going downhill, right, if my values are decreasing, if I'm going downhill, right, I should have a divider. Okay, so when I look at 18, 6, 2, excuse me, negative 18, negative 6, negative 2, right, I can see that I am dividing everything by 3. All right, so now since it's going downhill, right, it's decreasing, I know I need a number between 0 and 1, and since I'm dividing by 3, that number would be 1/3. And as I go downhill, I can see that I pass 3, then 2.3, 2.11, 2.03. I can see that I'm getting really close to 2. So if I take that and put it into my equation, it's 2 to the x. Oh, sorry. All right, y equals 1/3 to the x, and then plus 2. I almost reversed those. Okay, so my b is 1/3 and my floor is 2. Okay, so that was the review part. Now, here is what I was talking about earlier. So you want to highlight this page, star this page, all right, because this is information that you just have to know, okay? So exponential functions in real world problems, okay? Now we looked at this a little bit, all right, in lesson 2 for this unit, but now we're going to look at specific types of problems, all right? And those specific types of problems are exponential growth and exponential decay. Right, and these really are all the form of y equals a times b to the t, or x, depending on how it's written. Now, a is new. We've been looking at all of our exponentials so far as a being 1. Now, so what we're doing now is saying, okay, so this a value is not going to be 1, and that a value represents the initial amount in our problem. Now, b is still our multiplier, just like what we've been seeing, okay? What's going to change is how we find that multiplier, and that's where we get into exponential growth and exponential decay, all right? And then t is the amount of time defined in our problem. So that could be 3 days, 2 weeks, depending on the type of problem. So how do we find this b? Now, once again, if it's growth, that means our graph has to go uphill, all right? If it's decay, that means our graph has to go downhill, it has to decrease, so growth, decay. And if we go back to what we know, right, about exponential, we know if it's exponential growth, if it's going uphill, we know our b value has to be bigger than 1. So whatever our growth rate is, and that's what r represents, all right, the growth rate or decay rate, we're going to add that to 1. And that's going to give us a number bigger than 1, which is going to make our function go up or increase. If we need it to decay, we're going to take that rate and we're going to subtract it from 1. And notice that's going to give us a number less than 1, which means it's going to go downhill. Okay, now, a couple of details. We always want to write r as a decimal or a fraction, depending on the kind of problem we have. All right, so they give it to us a lot of times as a percentage. All right, and so if we have it as a percentage, we have to convert it to a decimal in order to add or subtract it from 1. And you'll see that as we go through some examples. And just remember, 1 is 1 whole, right? And if I multiply by 1, things don't change, right? It stays the same, which is why we have to either add to 1 or subtract to 1 to change that value. All right, so 1 equals 100%. All right, so the first thing we're going to do is just look at some problems and see if we can identify them as growth or decay. All right, so now notice we look at this problem. I'm going to look at my b value, which is this. Okay, is it bigger than 1 or between 0 and 1? So since this is between, or excuse me, this is bigger than 1, we know that this would be an exponential growth problem. It would go uphill. All right, now look at the b-value here, 0.97. Okay, that is less than 1. It's between 0 and 1. So that means it's going to go downhill or it would decay. Okay, then we look at 0.75. So just like what we just did, right, that is going to be a decay problem. It's less than 1. All right, and then we look at the last problem, 1.089. Okay, now that's bigger than 1. We don't care how much bigger than 1. As long as it's bigger than 1, it's going to go uphill. It's going to grow. Okay, now, so here's what we need to do next, right? So it goes back to this, right? So we have to write all percents as a decimal, right? So write all percent as a decimal. And there's two ways to do that. Okay, so the first way, all right, is understanding that, all right, a decimal means deci, which is from 100, right? So that's telling us out of 100. So 4%, right? So to change this to a decimal, what I can do is I can just take whatever the percent is and I can divide it by 100 on my calculator, all right? And that's going to give me the decimal, all right? So if I do 4 divided by 100, that's 4 out of 100, right? The decimal would be 0.04. Okay, and then that's how you get to your decimal. Now, what you might remember, all right, from your past math experiences is that you could shift the decimal places 2 places, right? So I could go 1, 2, and now that's 0.04. All right, I think that gets confusing sometimes, especially if you have lots of numbers here like this. I think the best way, if you're confused, is to always just divide by 100, and you will always get the right percentage changed to a decimal. So if I did 5.75%, right? So 5.75 divided by 100 tells me my decimal would be 0.0575. Right? And then once again, you can see that if you move the decimal place 1, 2, you'd have 0.0575. All right, and then 12%. So once again, I could do 12 divided by 100, and that'd be 0.12. All right, so remember, we just need to convert that percentage to a decimal, and that's what we're going to add or subtract onto 1 to find our new b-value. All right, so let's look at a couple of examples here. All right, let me flip the page here. Now, and here's where it gets somewhat complicated. And so let's read the first problem here. All right, scientists accidentally created 10 zombies in a lab and started the zombie apocalypse. Brand news. All right, unless you're, a Walking Dead fan, right? Then it becomes pretty good, right? They predict the population of zombies will quadruple every day. Now, notice we do have an initial amount, and that initial amount was 10 zombies, right? Okay. Now, is this growth or decay? Well, if it quadruples every day, it's definitely growth. Now, here's the thing. Sometimes, right, when I look at my forms here, the word might tell me what B is. And I don't have to go through all of this work, all right, to find the B, because sometimes I can recognize the word, all right? And in this case, the key word here, all right, is quadruple, all right? Quadruple every day. So if it quadruples every day, that means my base is 4, all right? So then, all right, I don't really have to worry about my growth or decay rate, okay, because the word tells me. If it said tripled every day, I know B would be 3, all right? If it said they grew by half, right, that's a little different. That gets a little harder. But when we see like quadruple, triples, doubles, we know exactly what that is. So now we can do A times B to the X. So my initial, all right, value, which is 10, and then times, all right, my function, which would be 4 to the X, like that. And there's my equation. So how many zombies would there be after 12 days? Well, I would do Y equals 10, and then I'd have 4 to the 12th power. And then once again, right, be familiar with your tools. So once again, the caret key here, that's your power key. So 4 to the 12th, all right, that's a lot of zombies. 1, 6, 7, 7, 7, 2, 1, 6, right? And then I have to multiply that by 10. And so we have a lot of zombies running around. All right, so you can see that those zombie population grew a lot in less than 2 weeks. All right, and that's what exponential growth really does, all right? So things grow really, really fast sometimes, or decays really fast. All right, so now let's look at number 7 here. All right, and then that might be all for our video today. All right, so it is estimated that there are 25,000 polar bears left in the world. All right, the population declines by 1/4 each year. So estimated there are 25,000 polar bears left. All right, so that would be our initial amount. Okay, and now the population declines, right? Declines by 1/4 each year. Well, if it's declining, that's decaying, it's going downhill. So we know this is decay. And our growth or decay rate is 1/4, right? So 1/4. All right, so now that's what our rate is. So now we want to write an equation. So this is y equals, and then if we go back, since it's decay rate, we want this, right? And we have to subtract that rate from 1. All right, so it's going to be 1 minus r to the t like that. Say our initial amount of polar bears is 25,000, and then 1 minus 1/4 to the t. All right, and if I do 1 minus 1/4, right, I get y equals 25,000, and then that would be 3/4 to the t. Now notice my number is smaller than 1, right? So I know this is decay. So you should be able to check that when you're done, right? So if it says decay here, I look at my b value. If it's not smaller than 1, I made a mistake. I need to go back and double check, right? Now 1/4, if you wrote this as a decimal, is 0.25. All right, so you could have done 1 minus 0.25, and that would have given you 0.75, which would have been equivalent. All right, so let's wrap this up by predicting how many polar bears will be left in 5 years. So 25,000, and then I'd have 3/4 to the 5th power. All right, so once again, let me just clear all that out. All right, and you could put that in 3/4, that's 3 divided by 4, and put that in parentheses just like it looks, to the 5th power. All right, so 25,000, and I'm just going to write 2 decimal places here. Now notice I'm keeping this in my calculator, and so I only write down 2 decimals, but I'm going to keep the number in my calculator, and then I'm going to multiply it by 25,000, and that's going to make my final answer, all right, more accurate. So what I can see is that when I do this, I do get a decimal here, 5923.61. And remember, we're talking about polar bears, right? So we just kind of round that number. So we'd say approximately, if you give that wavy equal sign, that means approximately, all right, 5,933 polar bears left. So you can see that's a dramatic decrease if it were really decreasing by 1/4 per year. All right, we'll do a lot more practice with this in class, right? But once again, right, really get to know, all right, this page. All right, if you have any questions, have those ready to go, and I will see you next time.